Okay, so we're talking about the homework problems and what it was causing some issues. So one of the classmates here said this is the approach that they calculated or used to solve for E of S. But remember what we said, E of S is just going to be equal to R, your input, times GH. The whole thing about open loop is you open that point. So R multiplies by your feed forward, this is G, multiplies by your feedback, this is H, and there's no summing junction here, right? It's disconnected it. So the error by definition is equal to R minus your feedback, which is R times GH. So your transfer function is your error divided by R is equal to 1 minus GH, correct? When I just factor out the R. But I'm looking for steady state error. So I take the limit as S approaches 0 of both sides. That term goes away. Well, S times this whole thing. The 1 times S goes away. So all you're left with is the limit as S approaches 0, S times GH. That's why the 1, you don't need to worry about it.
But then why did you remove the R?
I did the transfer function. This is my transfer function.
Oh.
Right? I mean, you're right. Technically, I shouldn't have factored out the R. Let me erase this. So technically, this is the transfer function for the error divided by R, which is 1 minus GH. If I actually want to get the error, I just have R minus R times GH. Now I do the limit function as S approaches 0. So this is going to be equal to S times R minus R GH. And then you have S times R. This is normally you can cancel it out, but if it's a unit step, you do have to include the 1 in there. But anything greater than a unit step, right, it's going to be 1 over. So it divides out the term. So all you need to do is use your K sub P, K sub B, K sub A. This is equal to 1 plus, off the top of my head, it's 1, I think is it 1 plus the limit? No, sorry. This is just equal to the limit as S approaches 0, GH. And then each of these, you just take the derivative of the previous one. So you just use your limit function to do that. You don't have to do any calculations. You just have to solve for your open loop transfer functions. People confused on this? Not confused?
Can you do the whole thing? The third question. I will step down.
The third equation, third problem?
Yeah, just find the ramp. Just the ramp. On the blank page.
Find a ramp? What do you
Yes, I'm putting down after you're thinking about the problem.
Oh, okay.
So I will think about it.
Let me delete all this stuff and I'll just paste it into whiteboard. If I can do it faster this way.
So you're saying you can't there at all?
There is no error, right? When you close the loop, you don't have error anymore. That's just the input to the output. The error, you need to keep a feedback path and it has to be negative feedback or else there is no loop. All right, let's copy this. And
It felt too easy when I got this type 0 system.
nope, not a type 0 system.
Maybe when it does like again feedback, it'll be involved.
You can just use G times H.
Yeah.
It doesn't have to be unity feedback.
I didn't want the ball 15. the if the load function is
Okay, so the whole thing about this work is we're going to be using our steady state error, which is ESS is equal to the limit as S approaches 0, S, S times GH, right? Now, we got to be careful because this is dependent on, what's happening in our system. So we have to go type 1 system, type 2 system, type 3 system, et cetera, because the input is where it has an impact on us, right? Because ultimately what we see is this is going to be, this has the steady state error also has to include the input in here, right? So that has to have that value of R that multiplies through. So the input is going to be a unit step. It's going to be a unit ramp or a parabolic. And what happens is the type system, which is the number of poles at S equals 0, is the system type. Right? That's our first sort of discussion point. So now, the reason why we need to know that is because depending on the input, we have an S over here, and we need to cancel out one of these S's. Otherwise, as our limit function approaches 0, then our equation is going to blow to infinity, because if we have a unit step input and we have no integrators, then our output is going to do something like, well, you're always going to have a steady state error, right? You're going to settle out over here. So you're going to have some sort of steady state error. If it's a ramping input and your output only has a single integrator, so your system is going to respond and it's going to go like this. This error continues to increase. So the reason why you need the integrators is to cancel out the fact that that input is continuing to increase. In effect, it's like integrating its own input. Because if I integrate 1 over S, I get 1 over S squared. If I integrate 1 over S squared, I get 1 over S cubed. So the number of integrators are going to allow me essentially to catch up to what the input is. Because the process itself is just going to respond to the input. But if I want to keep up, if I want to keep ramping up or parabolic up, whatever, I need to integrate it. So all I need to do, solve for GH, which is the open loop transfer function. We define that. And come on, let me go. Oh, it's falling asleep here, I guess. So the open loop transfer function is to go from this point back over here. Okay. We need to go back to this specific point. So my open loop transfer function is if I have an input over here and I get back to this point, all I need to do is go through G times H. So my G times H is 4 plus 10 over S. Multiply that by S plus 2 over S squared plus 4S plus 8. And then I multiply that by 0.05 over S plus 4. That is my open loop transfer function, but it's not really perfect because I've got this 4 over here. So I've got fractions and non-fractions. So all you need to do is put this under a common denominator. And now I can multiply them out. All right, so the system now has the open loop transfer function. I have the value. My next step is, how do I use the system? So I can do the steady state error. I can do the full derivation over again and do all the process, or I can take advantage of my tables. So I have a system type, 0, 1, 2, and then I have an input. So I have a step, a ramp, and a parabolic. And for a type 1 system, I can't ever force that error to be equal to 0. So I have to calculate a K sub P, and that's going to be equal to, what's the equation? Is it, What's that?
Do we have a table?
Yes. Let's look at the here. So for type 1 system, we have 1/1 plus, well, this is the error here. So let's click on this and let's see if it has, it doesn't give us the whole kit and caboodle. Try this one. This one actually doesn't tell us how to calculate the K sub P's. We're looking for one. Let's see, is this any better? The problem with this is it doesn't include the calculations for K sub A, because it just tells you it's a constant, but it doesn't actually tell you what that is. So let's see if I can find one that actually tells me values for K as well. This has one equation. So it would be nice if it actually had the included the K sub B's, but you can see that we have K sub B is equal to S times G of S. So we'll have to append our table and we'll recognize that K sub P is equal to the limit as S approaches 0. Let me zoom in a little bit, give myself a little room. The limit as S approaches 0, G times H. And then my steady state error is A over 1 plus KP, where this is the magnitude multiplier for our input. For a unit step, so we have to calculate what that K sub P is. For a ramp input, K sub P is going to be equal to 0, and ESS is going to be equal to infinity. Same thing for a parabolic input. So I don't have the ability to calculate what those values are. Actually, these are KV. And this is KA. So all I need to do is start to look for the table. Is this a type 1 system? Type 1 system has 0 integrators? No. I mean a type 0 system. A type 1 system, now we're going to calculate. So this one we don't even need to calculate. We know that K sub P is going to be equal to infinity, and ESS is going to be equal to 0. Over here, now we can calculate the velocity constant, which is just multiplying the position constant by S, or taking the derivative of it. So it's S times K sub P, which is equal to the limit as S approaches 0, S G times H. And then my steady state error is A over K sub V. And so now we got to do parabolic. In this case of A is equal to 0, and ESS is equal to infinity. You don't even need to calculate it. So what we do is now we know it's a type 1 system, so we focus in just on this row. And we see for a unit step input, we're going to get a steady state error of 0 and a K sub P equal to infinity. For a ramp, we're going to end up with a K sub B is equal to S times KP. This is a non-zero number. This is a constant. And then our ESS is going to be equal to A divided by KV. For parabolic, we're going to have ESS equals infinity. So you just need to use the table to do this. So going back to that problem, zoom out again a little bit. I've got a type 1 system because I have one integrator at S equals 0. So I use this table, which means I calculate K sub V, which is the limit as S approaches 0, S GH, which is going to be equal to 4S plus 10 over S, or times S plus 2 over S squared plus 4S plus 8. And that's time 0.05 over S plus 4. If you remember, we're going to multiply by S and take the limit of that as S approaches 0. So those S's will cancel, which is a good thing because the S, the zero in the numerator, the denominator would make that blow to infinity. So now all I'm left with is taking the limit as S approaches 0, 4S plus 10, S plus 2, 0.05, S squared plus 4S plus 8, and S plus 4. And remember, when you take a limit function, when S approaches zeros, all these terms go to 0. So what I'm left with is 10 times 2 times 0.05 all over 8 times 4. So let's see if we can do this in our heads. So we have 20 divided by 32, which is 10 divided by 16, which is 5 divided by 8. So 5 over 8 times 0.05, which is equal to, excuse me, I think that's 0.25 divided by 8. Let's see, can I figure it out even more from there? Probably not. So it's a quarter. Actually, no, it's 1/32, right? So that's what my K sub B is now. My ESS is equal to A, whatever the magnitude is of the ramp, divided by my velocity constant. It was 0.02 divided by 1/32. So 32 times 0.64. So all you have to do is look at the table. And if you remember, before, I think it was before break, we actually brought up the FE review manual, right? And we could kind of thumb through to look for controls. And that's what I said. If you look at and it's well, let's just put steady state error. I don't know if we exactly entered this, but if you look at the PE reference, and remember, I think we even went to this Mississippi State one. Yeah, it even brought us to the right page, 231, which is where we're looking. So this table, we actually showed that in class. I think again, it was before break. So it shows you a type system, 0, 1, 2, a unit step. They just call it K sub B. So they don't do a good job because this K sub B value changes, right? K sub B, I can't write on it, but K sub B varies. So for a step input, it's different than a ramp, and it's different from a parabolic. K sub B here is equal to the limit as S approaches 0, GH for a unit step, or it's the limit as S approaches 0, SGH, or it's the limit as S approaches 0, S squared, GH. So this K sub B value that you see here, it's not necessarily specified. But even over here, it talks about the open loop transfer function. It even shows you how to do this. Although this is incorrect as well, because this right here, well, no, I'm sorry, this is correct. They've actually factored out the S terms. You can see that you have S terms in there. So that's maybe why or how they do it, but it doesn't really give you a good way to get it from this table. But yeah, we use this table to go ahead and calculate that. Questions? Cleaning up the cobwebs from 2 weeks ago? Any questions before we start on new material? Does this answer what you had for a question, Birdzilla? It should not take you 4 pages of notes. It should be.
Yeah, not a lot.
Yeah, don't calculate the closed loop transfer function. That takes a lot of time. All right, root locus. Let's see, where can I get this out of my way? All right, so we've already done a root locus. We talked about it in one of the labs, right? Is there a way of plotting it? So we kind of understand the concepts and we've been mentioning it, but it really kind of hammers home a lot of what we've been doing. But the whole point of a root locus is you're plotting all, now we're going back to closed loop, all closed loop pole locations. It actually plots the zeros too, but we really are only focusing on the poles. So we'll actually call those the poles. And you can control or you can adjust one parameter, a value of K, which is a constant, and it's a real constant. So here's our value of K that is in our closed loop transfer function. And we want to see how we change that value of K to get different roots. Remember, it's the roots are in the denominator. This is the characteristic equation, which determines the response in the time domain of our system. So if we want to have a fast system or fast decaying system, we want to be as far away from the real axis as possible. Remember that whole concept where we talked about time constants, where we had e to the minus t over tau. So that becomes e to the minus t times a. So that means that a is equal to 1 over tau. And if you recall, we have s plus, a is our pole. So if we want to have an A way over here, then this, let's say it's a value of 10. Well, our time constant is just equal to 1 over A. So it takes 0.1 seconds. So a faster decaying system means getting far away from the real axis, right? We talked about that. So if we have performance criteria where we're trying to get some sort of characteristics, we can plot the roots all at one point. So let's take a look at that characteristic equation, but now we're going to allow K to be variable. We'll start out with K being equal to 0, and K is always a positive number. Anybody want to guess as to why it's always a positive number? You probably have a pole in the right-hand half plane. The other thing too is if you're designing a real-world system, is there such a system that you can have a negative gain? I mean, we can do it in electrical circuits all day, right? We can invert things, but in the real world, you're not going to design a mechanical lever that has a negative gain, right? That would mean something in the opposite direction, or you wouldn't even include it in the first place. So it wouldn't be practical. So we'll start at 0, and here are our closed loop poles. Well, this one actually shows one of the term vanishes. And so we talked about actually having it where it's an unstable system. This is an unstable system because look at the poles. We have 2 poles on the right-hand half plane. Now let's do 1 at 1. So now we have a substitution for K equal 1. Now we've got some closed loop poles, and these are all in the left-hand half plane. Continue on. Here's 2. Still looking pretty good. Here's 3. And here's 4. And so, whoops, I thought I had 5. So now we can plot these, right? And it's a little bit hard to tell, but the direction, if you can see, it started over here and here, right? Because that's the 0.3 minus J5. And it starts to head in this direction, right? We also have one that goes over here and heads in this direction, right? And so what we're seeing a little bit is we're seeing how as we vary this value of K, it's moving our poles around. So what we want to do is instead of having to do this calculation where we had to calculate 6 closed loop poles, and this is just 6, we want to go ahead and automate the process that we can calculate all the poles or have the ability to draw what the poles would be on and where they would locate. Oops, let me, so you can actually see it where we drew it. Let me kill this real quick. Let me erase my. Let's go back. Let's try that one again. So we'll do the animation. And we'll actually see them moving. So here's where they start with k equals 0, and they start moving towards each other, start heading towards the real axis. And you can see the gain value is increasing. If you look at the top, you can see the details, it's going down. Now they start to go away from each other. And once those x's get pretty close to each other, they start to get away and just kind of go off into that region. So we want to automate that stuff. So let's look at this transfer function first and figure out why do we want to do this? Well, remember our second order transfer function has this general form, s squared plus 2 zeta omega sub n plus omega sub n squared. Zeta is the damping coefficient or damping constant. And this is the undamped frequency, right? So what we'd like is we draw our axes. Do you all remember how we got these parameters here? This is our j omega axis and how we get this plot here. Hopefully you all understand. Where do I get those? It's just from the quadratic equation, right? Negative b plus or minus b squared minus 4ac all over 2a. That's how we did that. And then we ended up solving for that. Does anybody need me to do that again? Or do you feel pretty comfortable about how we got this? Okay. So now we have negative zeta omega sub n plus or minus j omega sub d. Omega sub d is our damped damped frequency. So all I'm going to do is plot those roots on our pole 0 map. And so what I see is this is j omega d and minus j omega d. And here is the real part, minus zeta omega sub n. Well, we love doing triangles, right? So is there a way of calculating what that angle is? Do you all remember? Pardon? SOHCAHTOA? We'd like to do SOHCAHTOA, but we can't quite do it yet because we don't really have a hypotenuse. So how would you solve for the hypotenuse? Well, it's not the j term, right? We have to take the j term out.
Oh,
Then this whole thing is square rooted. So if we do our math, we have zeta squared omega sub n squared plus omega sub n squared times 1 minus zeta squared. Hopefully what you see is this term cancels with this term, and what we're left with is omega sub n squared, square rooted, right? Which is just omega sub n. So this here is equal to omega sub n. See the math? Now I can go ahead and I can do SOHCAHTOA if I want. So what is this angle right here, theta? Just a trig identity, right? Oscar had a heap of apples. So I have all sides. Well, let's do it with the hypotenuse because we just calculated it. So the cosine of theta is equal to what? The adjacent over the hypotenuse. And remember, we don't worry about the negative signs, right? Because now we're just talking purely imaginary. So the cosine of theta is equal to zeta. So cosine of theta here, or the inverse cosine of zeta, is equal to theta. Which is going to allow us now that if we have some ability to draw this line as an angle, what does that tell us? If we stay under here, what happens to zeta? Can you tell me? How do I stay below that line? What does zeta need to be equal to? Less than 1. So let's just say that this is 45 degrees. Let's make it easy. How do I make sure that that theta is less than 45 degrees? Does everybody remember that? We talked about that, I think, in this class, or the previous class. So is this the cosine of 0 or 90 degrees? Square root of 0 over 2. Cosine of 0 is 0. Cosine of 90 is 0, right? So this becomes cosine of 60, cosine of 45, cosine of 30, and cosine of 0, right? So how do I make sure that I'm less than 45 degrees? Zeta has to increase. It starts at 0 if it's straight up, and then goes in this direction as zeta increases. It goes up in magnitude. So what we say is by staying under this hypotenuse, under that angle, then we have less percent overshoot, right? Not right? Because if you remember the equation, and I won't remember it, but maximum, why is this writing? Okay. Maximum percent overshoot is equal to E to the minus, and this is where I struggle, pi times the square root of, I don't know, you can look that up because I can't remember that off the top of my head. But you remember this was all dependent on zeta. So maximum percent overshoot is a function of zeta. And as we increase zeta, we had less percent overshoot. Remember those curves where we had a lot of things spinning up and down? So that actually validates here. Less percent overshoot means we get closer and closer to 0. What happened, or closer and closer, yeah, at 90 degrees, I should say, or 0 degrees. What happens when the cosine is 0? You're at the cosine of 0. What happens to zeta? Pat's got it right. It's got to be equal to 1. And what happens at that zeta equal to 1? It's critically damped or over damped, right? So it's no longer a second order system, which makes sense because at that point, how many complex poles do we have when it's no longer under damped? None. So that makes sense that we want to be on this axis because we're down, right? We only have real poles at that point. We have no complex poles. So we can use this as a design tool to say, all right, I want my percent overshoot to be less than 15%. I can calculate this angle of beta that corresponds to a percent overshoot of 15%. And as long as I'm on this side of the curve, on both sides, right? Because I also know that because I have complex conjugates, I have to have one over here. As long as I'm on that side of the curve, then my percent overshoot will be less than 15%. So I can use that as a design criteria to say, I want my percent overshoot to be 15, but I also want it to have a settling time of a certain value. And that would be indicating over here on the real axis. And so that's how you'll design it. You'll plot your locus and have all these points. I might have to erase a bunch of this stuff because, yeah, so let's go ahead and erase these. I love doing this cosine thing. I don't know. I was taught it in high school or college, and I still remember being taught. And I was like, wow, that just changes a lot my world, because I could never remember the values. And I can remember having to take tests. They wouldn't let you use calculators and you have to memorize cosines and sines. But once I saw that, I was like, oh my God, it's just, you don't have to memorize it. It's just, that's much easier. I think so. Come on, keep erasing. Okay, so what is the line of constant settling time? Up and down, right? The zeta is determined the real part, and that determines how quickly it reaches steady state. So that is just on the real axis. What is the line of constant zeta? Zeta is going to be that angle that goes away from the origin, and that's going to tell us our percent overshoot. You can see I have the blue line, but also down below it's the same line. What is the line of constant omega sub d? That's our imaginary part is constant. Usually that doesn't work for us so well, but the first two for sure. What about constant omega sub n? That's going to be the diameter of the unit, the circle, right, where it reaches out. What is the line of constant tau? It's the same thing as item number 1, correct? You just have to invert it. And what is the line of constant percent overshoot? It's the same thing as line number 2, right? Where we have zeta being equal to constant. All right, so I'm going to get you back into some math. So I'll do it this way, and then I'll give you an in-class example to do it for me, okay? All right, so what is, this is our graphical representation. We want to see if a point, we pick any point we want, in this case, -3 plus J4. We want to see if that is on the root locus. And on the root locus has a magnitude of 1 and an angle of plus or minus 180 degrees. That's always the case, and you'll see that in a little bit. But let's do some math. All right, so the first thing I'm going to do is I'm going to check and see if this equals 1 at an angle of plus or minus 180. So I have my transfer function, my closed loop transfer function in this case, and I'm going to evaluate that at s equals -3 plus J4. So this has to be substituted in there. So now what I'm going to do is I'm going to break numbers apart, because what is it about complex numbers? Was there a cheat sheet or easy way to go ahead and multiply and divide complex numbers? Y'all remember that? So when you multiply complex numbers, multiply the magnitudes and add the angles. And when you divide the magnitude and subtract the angles. Does that ring a bell? I do this a lot in my classes, but some of you haven't had a lot of AC circuits. So this is a pretty important one. If you can't do this, you're going to really struggle to understand how to calculate magnitudes and angles. Is it anything I'm doing here fancy or not what you've seen in the past? You could say no or yes, it doesn't hurt my feelings.
So the -3 plus J4, what do you do?
I haven't done that yet. I'm just doing this generically. I'm just saying, let's pick a point, -3 plus J4, and we want to see if that's a valid root locus point.
Oh,
But to check and see if it's a valid root locus point, I need to be able to do some complex math. This is the kind of complex math that you're going to be expected to do. Okay. All right, so if you're okay with that, let's go ahead and actually start finding magnitudes and angles for these numbers. So I'm going to plug in -3 plus J4 in for S. And if I evaluate the numerator part, I get square root of 20 at an angle of 117. Why did I put e to the j 117 there? Because if I want to do it MATLAB, it works really fine. You're also perfectly fine to say this. You can pick whichever way you want to represent it, but I know some people with their calculators. By the way, Pat, did the TI calculator that you used this weekend, could you enter complex numbers in?
I don't know.
Okay. It'd be curious if you could actually enter them in this way. A lot of those cheap calculators, you don't have an angle symbol, but
On the
you
TI, you
can,
can.
if you enter
There's
E,
an angle.
J, whatever, they might be able to do the calculation that way. maybe, I'm not sure.
They were small enough where it was.
Could do it yourself. Did it have the I function on the calculator? Most calculators can do basic complex numbers, and they would include I. If not, that's okay. Okay, so we got that one. Now let's do it for S, 5 at an angle of 127. We'll do it at S plus 2. Square root of 17, e to the, at an angle of 104. Now we do all those at once, and all I did was I just put these numerator, denominator, denominator, and I ended up with this final number over here. So does this equal 1 at an angle of plus or minus 180? 0.22 at an angle of minus 114? The answer is no, it does not. So if I was to go back to, actually, I don't have this one plotted yet, so we'll go forward. We can't get there from here. So the magnitude to get to from minus 1 is square root of 20. And then the angle is that whatever that 114 minus 114. So this angle here would be minus 114. We also can do one over here. Actually, not that one. It's the wrong one. Let me go back up. This one over here, the magnitude and the angle I get from here. So this is 117. Now I'm going to go from my pole at S equals 0. Magnitude is equal to the square root of 25, which is 5. And the angle here is 127. And then the last one I'm going to do is from S plus 2. So the magnitude, or S minus 2, sorry. So this magnitude right over here should be equal to square root of 17. And this angle is 104. Anybody have any hardship that these are all plus? I'm rotating in a counterclockwise direction, right? So I go 104 degrees in this direction. So when I sum all those together, that's when I end up with 0.22 at an angle of 114. You can plug this into MATLAB and you can see what you get. Gonna get something like this. So one thing we'll say about root locus is they are symmetric about the real axis. Why? Because you have to have complex conjugates. You can't have a plus j conjugate. Oh, it's got the D in here. Sorry about that. So you can't have a plus angle or a plus j without a minus j. All right, your turn. I'll give you 5 minutes. You tell me what these need to be. 5 minutes. I'll pause the recording so people aren't going to fall asleep. All right, everybody get the answer? You got it? What's that? All right, so there's 2 ways you can do it. You can do it the individual way. And let me just double check. So it's -2 plus j. -2 plus j. That is the one we want to check if it's valid. So we're going to do the first one. So we're going to have -2 plus 3 plus j, which is equal to 1 plus j. Item number 2 is going to be -2 plus 4 plus j, which is 2 plus j. Number 3 is going to be equal to -2 plus 1 plus j equals -1 plus j. And number 4, -2 plus 2 plus j is going to be equal to j. So this one's 1 at an angle of 45. 1 at an angle of, let's see, it's -1, and it's J, so that's, what angle is this?
-1.
Just tell me what the angle should be.
1.
You could do that in your head, right? Because you just have to do the axes. And what's this one? 1 at an angle of 90. The 2 over J, I can't do that one off the top of my head. Anybody help me out with that?
2.3. Square root of 1. So 1.4. Yeah, square root of 2.
Oh yeah, square root of 2, yeah.
Then the one is +1 -1 plus b. Oh, yeah.
Yeah, the J is just 1 at an angle of 90. So now all I need to do, square root of 2 at an angle of 45 times 2.23 at an angle of 26.6. Oops. Divide by square root of 2 at an angle of 135 times 1 at an angle of 90. That's going to be equal to square root of 2 times 2.23 divided by square root of 2. And the angle is 45 plus 26.6 minus 135 and minus 90. So that's equal to 2.23 at an angle of, let's see, so 153. Okay. Now there's a couple ways we can check that. You can just plug that into your MATLAB calculator. The other way to do it is just to plug them in like this and just say, all right, I have -2 plus J plus 3 times -2 plus J plus 4 divided by -2 plus J plus 1 times -2 plus J plus 2, right? You can always do that. And then what you end up with is, and I don't know if this is any faster, it may or may not be. So 1 plus J times 2 plus J boy, oh boy, divided by -1 plus J times -2 or 0 plus J, right? Now this way always works, but here's what you have to do. You have to do a bunch of FOILs, and then you have to multiply by complex conjugates, right? It's a lot of work, isn't it? So you can always do rectangular coordinates and do multiplication and division, but you can't divide complex numbers by each other, right? What do you have to do? You have to get rid of the complex number in the denominator by multiplying by the complex conjugate and then dividing by real numbers only. Does everybody understand that process? So this is why you don't want to do this. But if I want to check if my work is correct, let's go to MATLAB. I might have closed it because I'm using so many resources. Every time I have MATLAB running in Zoom, this computer is over 3 years old and it just eats. It responds really slowly.
With that 2 plus J, keep that angle 26.6. Is there anything you can do for that, or is it just kind of
You get the 26.6? The only way that I would estimate it is if I did this. So I would draw a picture. I got to go 2 here and 1 here. And here's my corresponding vector. So it's less than 45, but how much is it? I don't know, you know what I mean? So, I mean, even if you tried to calculate the hypotenuse and then just did the inverse cosine, you'd be struggling, because we know over here that this is going to be equal to the square root of 5. And so then we could say, all right, well, the sine of this is equal to 2 over the square root of 5. And you know what I mean? You just keep digging down. And so there's no real way, because we do know that this is also supposed to be equal to the square root of 1 over 2, which translates into 45 degrees. So we know it's less than a half. So it's less than 45. Actually, no, is it, it's less than 30, sorry. So we know it's less than 30, but how much less is it? You know what I mean? You could just say it's between 0 and 30, 30 and 45. So you can get some refinement, but at this point, you're not really getting any efficiency. Unless if you're really efficient, you can use probably go to your fraternity and they have them there. Slide rules? Anybody know what a slide rule is? I've never even been taught one, and I'm 53. I don't know how old your dad is. Maybe he might be a couple years older. They went out in the 70s. So even when I went to high school and we started using scientific calculators, that wasn't I started in 84 in high school. They didn't even mention slide rules. Slide rule is basically calculated before the calculator was around. You had to do all calculations with logarithms. And on the slide rule actually were sine and cosine tables. So you could do these basic ones of 30, 45, 60, 90. But to do any with other ones, you actually had to use your slide rule and use that. It just had the information, so it was stored there. So I don't know, that was slide rule days. The only time I've seen one, there was a guy I used to work for. Must be in his 80s now. He actually had a slide rule, but he never even used it. He just kept it as a memento. He always used his calculator.
Oh, the one with one.
What's that?
This, yeah.
No, different.
That's the one. I thought that was.
All right, so let's do this one. We'll just say S equals 2 plus J, right? Just make sure that's our minus 2 plus J, sorry. And then we're going to say G is equal to S plus 3 times S plus 4 divided by, and I'm going to use double parentheses because I need to have a whole one here, S plus 1 times S plus 2, I believe. Now, this should be equal to, if we did our math correctly, 2.23 at an angle of minus 153.4. But it won't be because MATLAB does everything in polar coordinates or rectangular coordinates. So I do the absolute value of G and the angle of G times 180 over pi, 2.23 or 2.24 at an angle of minus 153. Exactly what we expect to be able to get. Okay. So where's PowerPoint? Here we go. All right, so now we know how to do that. So now we're going to go ahead and actually set up the root locus and see why our system has to be equal to 1 at an angle of plus or minus 180 degrees. We're going to assume that this value is positive for obvious reasons, right? We don't want negative gain. So here's our closed loop transfer function with our value of k in there. That becomes 1 plus our open loop transfer function. And then our characteristic equation is only going to be based on 1 plus our open loop transfer function. We actually don't care about the closed loop transfer function. We only care about the open loop transfer function because this is our characteristic equation. And as we've mentioned, even at the beginning of this class, our characteristic equation is what's going to give us our output. It's going to characterize what the output is. So every valid point, every valid root that we guess, or every point that we guess on our whole zero map has to validate this question, 1 plus k gh, right? Because the definition of a root is an S so that the CE equals 0. This is a requirement. So that's why we set that equal to 0. So remember what I said about the magnitude? Magnitude of our valid root has to be equal to 1 at an angle of plus or minus 180. Why did I say 1 at an angle of plus or minus 180? No? No? You're staring at the answer. Isn't -1 equal to 1 at an angle of plus or minus 180? Yes? Like I said, it's kind of obvious, but it's there. All you need to do is make sure that the magnitude is 1 in the angle for this equation to be valid. That's where we came up with it. And that's why we spent time validating. So the magnitude, so you can use that to solve for K. Any value of K is going to be equal to 1 over GH. That's the magnitude. And the angle, so this is different. This is the angle for that has to be 180 plus or minus 180, 3 times plus or minus 180, and on and on and on and on and on. And it's only going to be odd multiples of 180. Why odd multiples? Because what are even multiples of 180? $360, $720, on and on and on. Is 360 the same as 180? 360 would be a positive one, not a negative one. So it has to be equal to plus or minus 180. So that's why these are always odd multiples. Okay. All right, so let's rewrite that equation to start by looking at our poles and our zeros. So in our characteristic equation, we have an open loop transfer function, G. So this here is G. And inside of G, we have poles and zeros. So we're going to express that as a numerator and a denominator. And the Z's are going to give us the zeros of the open loop transfer function. And the P's are going to give us the poles of the open loop transfer function. So we're going to go ahead now and multiply both sides by P to get rid of the denominator. And what we see is our P of S times our K times Z of S is going to be equal to 0. So let's let K equal 0. If we let K equal 0, then our characteristic equation just becomes P of S equals 0, correct? Yes? What about K equals infinity? Let K be a really big number. What happens to this equation P times K ZS? So let's rewrite it. The limit as K approaches infinity, P of S plus K Z of S. What happens? Goodbye to the poles, right? P of S equations, because as K gets bigger and bigger and bigger, it dominates. You can neglect any of the P stuff. So our characteristic equation becomes K times ZS. Interesting. So remember I said this mantra about root locus? The root locus starts at the open loop poles and ends at the open loop zeros. Do you remember when we talked about finite poles and finite zeros? And they always have to be they can be different, but when you include infinite zeros, they're always the same. Well, this is the primary reason why I've been harping on this. Because if your root locus starts at a pole and ends at a 0, don't you have to have the same poles and zeros when you include all the infinite zeros? So to help you with a root locus, memorize this. You start at a pole and you end at a 0. Start at a pole, end at a 0. So when you do a root locus plot, or when you just do a pole 0 map, I'm starting at a pole and ending at a 0. I'm starting at a pole and ending at a 0. I'm starting at a pole and ending at a 0. So the root locus, all valid plots, root loci plots here, live between these two, and these two. Okay? Very, very helpful. This is when I was learning root locus. I remember I had this aha moment, if you will, where once I realized, what am I doing on time? Once I realized that your poles indicate the starting point and your zeros indicate the ending points, you actually can start to see, all right, am I getting to a 0? So when you draw a basic pole 0 map, you can get an idea in your head, what do I need to calculate? Because there's a bunch of things that you may or may not need to calculate based on looking at our poles and zeros. All right, so here is our pole 0 map for the example that we did where we calculated those magnitudes. So we have 2 poles and 2 zeros, 2 finite poles and 2 finite zeros. So here's our closed loop transfer function. Here's our characteristic equation. When k goes from 0 to a very large value, here's what we're going to do. We start at our poles. Uh-oh, we didn't end at a pole. So we have to exit the real axis. And look what we're doing. We're exiting, and it looked like we were going off to no man's land, but we're actually starting to curve around. Why is that? Because we need to end at zeros, and we don't have any infinite zeros. We only have finite zeros. So you can see how we're ending at zeros. Okay, and you can get, as you go all the way up to 200, it just gets closer and closer to that. Do that again. Start at poles, really small numbers. They get closer and closer to each other, but they can't end at each other because I'm not ending at a pole. So I have to deviate. I have to deviate from my real axis, and you'll notice I deviate by doing complex conjugates. You notice that there's a positive one, there's a negative one. Once I get on the real axis again, I don't have to worry about conjugates. I can go in any direction I want. So that's why, if you'll notice, this root locus here, I wish it would have stayed, but anyway, that root locus goes in that direction. The other one goes in this direction. This one could go this way, and that one could go that way, but they could alternate. You don't necessarily know. You have to do some additional calculations, but you don't really care because they basically almost touch each other, and then they go in opposite directions. Actually, they do touch each other, and then they head in opposite directions. And the reason why they touch each other is because you've gone from an overdamped system to a critically damped system right when you're leaving the real axis. Once you've left the real axis, you're now underdamped. So they would be going at separate points. Yes, sir.
When you had the saying that it starts at pole and 0, it was saying that those are open loop poles and zeros.
Those are always the open loop pole zeros, because the characteristic equation is just looking at the denominator, right? And that was the 1 plus g, not the g over 1 plus gh. It's just 1 plus gh. So it's the open loop transfer function that we're focusing on. Okay. All right, so this is just a summary. What if we have more finite poles and zeros? Well, here are zeros at s equals infinity. Oops. So your zeros at s equal infinity is the difference between the two. And n is the order of the numerator, the denominator, and m is the order of the numerator. So you can see as I start to approach, I end up with this negative k times b sub n. So that still equals 1 at an angle of 180 degrees. So I will start at a pole and always end at a 0 when I include the infinite poles. Okay. So that's this approach over here. When we take the limit function, we just end up with that, and we can go ahead and do this process over and over and over. All right, I'll stop here. I'm just about out of time. No lab this week. I talked to Conlon, and we just figured we're not quite ready for a root locust lab tomorrow. And I said, if you want to do a study session, he goes, you guys need a break. I don't know if that's true or not, but he said no lab tomorrow. So I said, it's fine with me. So you get Wednesday to relax for a change. All right, questions. We'll pick up. We got probably a couple more discussions on root locust, but once we finish up with the root locust, that'll be the last material we'll cover on the third exam. So steady state errors and root locust plots. Any questions?
Is there a home upgrade scheme as well?
I think there is, but I can't look without letting the whole world, I don't know where. Is it what it's available for?
So always saw this.
Yeah, I think I don't remember when I made it available, but I did have it coming online. Post haste, but the solutions for homework number 8 should already be available, correct?
Oh, I think they're available.
They were available at 8 this morning, I thought. If I had that set up right, but
You had it set up like at the end of class.
oh, 9:30, okay. All right, any questions from TV land? All right, have a great day, and I will see some of you shortly, some of you not till Thursday. Take care, everyone.
Thank you, Paul.